Well, hello Internet, and welcome to my probability course. In this one video, you're going to learn pretty much everything you could learn about probabilities from a 500-page textbook. It includes numerous formulas with real-world examples that demonstrate every single formula. And if you pause your way through it and take notes, you will have a solid understanding of probability on a very deep level. And if there is a lot of interest in this tutorial, I will continue to create one for statistics, linear algebra, and calculus, and completely cover the math of machine learning. So probability basically focuses on finding the chance a random event will occur over the long term. Probability is a number between 0 and 1, but also is represented by percentages. And a basic probability can be found by dividing your preferred event by all of the other possible events. For example, a coin flip has a 0.5 probability of coming up either heads or tails. Now, to find all possible outcomes, if you would roll 2 dice, what you would do is multiply 6 times 6 to get a total of 36. And you can see here all of the probabilities of rolling 2 dice. Now, this is a very important slide to understand because I'll be using it many other times across the course of this tutorial in multiple different examples. Now, if you see the symbol PA, this simply stands for the probability of the event A occurring. A set is going to be a list of all possible outcomes. And if we decide we want the union of 2 sets, we create a set that contains all values in either set. And you can think of the word union as being similar to the word or. And you can see here is the symbol for union. And if the value is in set 1 or set 2, it is of course going to be part of the union of those 2 sets. An intersection, which is like the union symbol flipped upside down, whenever it is used with 2 sets, will contain only values in both sets. And like the union, the intersection is going to act like an AND condition. So you can think of the intersection symbol as the word AND, meaning that the values are in both sets. So for example, and then finally, if you have A with the values 1, 3, and 5, and a set with all values from 1 through 5, the complement of A would be 2 and 4, because those are the values that are not in set A. Now, conditional probabilities deal with how probabilities change given other events occur. For example, what is the probability that a die roll is 5 given, this symbol means given, that we know the die roll is an odd number? To find the answer, all we do is divide the probability of rolling a 5 using a 6-sided die, which is given a probability of 1/6, by the probability of rolling an odd value, which has a probability of 1/2. And whenever we do that, we see that given we know the value is odd, there is a 1 in 3 probability of rolling a 5. Now let's use the conditional probability formula again. Let's say I have data on 200 men as well as women who exercise or not. Now, if I randomly picked a person that exercises, what is the probability that that person is a woman? To find this, I take 17 over 200, representing the women that exercise, and divide that by the total people who exercise, which is going to be 39 over 200. And if I do this, I find that there is a 43.6% chance that if I pick a person that exercises, that person is going to be a woman. And this over here is called a contingency table, and it contains all of the probabilities depending on multiple different outcomes. And intersections between the rows and columns provide joint probabilities between those events. Now, in this example, what I want to do is I want to find out if a randomly chosen person is a woman or an exerciser. And for this, we're going to use what is called the addition rule. Now, if two probabilities are exclusive, we are going to add them. But in this case, it is possible for someone to be both a woman as well as a person that exercises. So to find our answer, I must subtract out the intersection of women as well as exercisers. And you can see that subtraction taking place right here. And so, as you can see, there is a 0.61 probability that a random person will be a woman or an exerciser. And this is an example of what we call a joint probability, because we are looking for a person with two characteristics. If we said we wanted to look at exercisers and then from that group pull out just women, that would be an example of what we call a conditional probability. Now, probabilities can be either dependent or independent, meaning whether they affect each other. And to find dependence, we want to find if the probability of A given B, remember this line means given right here as well as this, is going to be equal to the probability of A and vice versa. So if they are dependent, and so in that situation, they would be dependent. So if we know that the probability of a die being odd affects the probability of a dice roll, and we see dependence, however, a die being odd doesn't affect the probability of a die roll for either an even or odd dice roll. Now you're going to find probabilities of independent events and dependent events in different ways. Now, if an event is independent, what we're going to do is multiply their probabilities. For example, to find the probability of rolling a 1 and then a 2, both who have a probability of 1 in 6 or 0.167, we're going to multiply them to find a probability of 2.8%. Mutually exclusive events, however, can't occur at once. So with them, you add their probabilities. So to find the probability of rolling a 1 and then an even number with 2 dice, what we're going to do is add 1/6 plus 1/2 to get 2/3. And as you can see, that makes sense because 4 values out of 6 is equal to 2/3 in this situation. Now, Venn diagrams can be very useful for representing events and how they interact. They work best for marginal probabilities, being probabilities that don't affect each other, and they also work very well with joint probabilities, which measure the likelihood of events occurring together. They don't, however, work well with conditional probabilities and when analyzing sequences of events. And you can see here all the symbols you have seen so far work together in one Venn diagram. And down at the bottom of the screen, right here where we have the C, this is going to represent the complement of the event. And here what I'm going to do is use our previous exercising table in a Venn diagram format. And you can see how the table data translates over from our table into our Venn diagram. Now, tree diagrams are normally used whenever Venn diagrams cannot be used, and they work best with multi-stage and conditional probability problems, which is the opposite versus the Venn diagrams. They, however, work poorly when events take place at the same time. And here what I'm going to do is break down the process of flipping a coin twice. And you can see that we can find just by using this tree diagram that probability would be 0.5 for each of the individual coin flips and 0.25 whenever we include both coin flips. Here also, just to cover something a little bit more complicated looking, is a tree diagram that's going to represent the different toppings you can have on a hamburger. In this situation, you can see that there are 16 possibilities with a 1 burger option, which of course would double by adding another burger to our equation. And as we continue, we'll get into ways that this can be more helpful whenever we deal with things called permutations, combinations, and variations. Now here what I'm going to do is find the total probability based off of 2 options. To find it, what we're going to do is some probabilities where we multiply the probability of A given B by the probability of B. Now in this example, we have two options of brake pads of differing quality. You can see here, brake pad X is going to give us 40,000 miles 95% of the time, and they control 60% of the market, while brake pad Y is going to give us 40,000 miles 92% of the time, and they include 40% of the market. And what I want to do is calculate, if I buy a random brake pad, that it is going to last 40,000 miles. Now we find the probability of a random purchase allowing us to travel 40,000 miles, and we can see here that that works out to 93.8%. And anytime you want the marginal probability of multiple different events that are identical, what you will know that you are looking for is what is called the total probability. And here, just to reinforce this, is another example. If I know the satisfaction ratings and the percentage of market share owned by different car insurers, I can find the probability that I will be satisfied with my car insurance. And all I need to do is add up those values, taken from here, this being the percentage of market share owned by each of the different companies, and over here where we represent the percentage of customers that are satisfied or dissatisfied. Add all those up and get 86.97%. Now, Bayes' theorem is going to be used to find a probability when we know other probabilities. And it comes in two forms in which I will demonstrate both of. Here's one form, here's the other form. Here, I'll find the probability that if I know I have an exerciser, meaning a person that exercises, what is the probability that they are a man? Now, I'll take the data from our chart, and then I plug it into Bayes to get a result of 0.564. And then I can double check my work by finding my results equal 22 over 100. Now I'm going to use another form of Bayes here. If 3.98% of people are infected with a disease and 98% with the disease test positive, and there is a 1% false positive, what is the probability that I am infected if I check positive? Well, to figure this out, I multiply the probability of infection by the probability of testing positive, given that I am infected, and then I sum the product of infected as well as positive tests by the product of non-infected by false positives. I then divide and find that there is an 80.9% chance that I'm infected based off of errors in the test and the low probability of people that are infected. Now, the Bayes theorem is super useful, so I want to give you another example of how we can use it. Here we have 3 toy manufacturing machines, and each is going to make different quantities and a known percentage of flawed toys. And what I want to do is figure out, if I know a toy is flawed, what is the probability that it was made, in this example, by machine C. Now here, X will represent the event that machine A, B, or C made it. Y then is going to represent the probability that the toy is flawed based on the machine. And I'll then find the sum of X multiplied by Y for each machine. And I'll find the product of flawed toys from C by the percentage of toys made by C. And then you can see here, after I divide, I find that there is an 11.69% chance C made the toy if I receive it and it is flawed. Now moving on, Combinatorics is going to be concerned with the number of ways items can be ordered, and they include permutations, variations, as well as combinations. Permutations focus on the number of ways items can be arranged, and you find them basically just by taking the factorial. For example, there are 24 ways to arrange 4 items. And we find that by multiplying 4 times 3 times 2 times 1. And you can also see in the pictures on the side how those break down. Now you're going to be able to find the number of permutations of X items chosen from a list of N items as well. Once again, you're going to use the factorial. And you can see the formula that we have right here. So in this example, if you were picking 3 runners for a relay race from a group of 5, you'd find that that is going to provide 60 permutations. However, maybe a more interesting example would be, what is the probability of drawing the numbers 1 to 5 out of a possible number of 15 numbers? Now, to save time, you can also come in here and cancel out the factorial of 10 from the top as well as the bottom to get 360,360 permutations. And then if you would go on to divide 1 by that number, you find that it is extremely rare, which would come out to 0.00000028. Now, when calculating combinations, the order is not going to matter. And here I'm going to cover combinations without repetition. And this means a value can only be used once. You can see here the formula that you are going to use to calculate the combinations, where X is going to represent the number of items chosen, and N is going to represent the total available number of items to pick from. And whenever we calculate the number of combinations, when we want 3 numbers from a group of 10 without repetition, we find that we get a value of 120. So there's 120 combinations if we define those rules and follow them. We can also find combinations with repetition. And you can see here the same exact formula we had before, where N is the number of items to choose from and X is the number of items to pick. This time, we're going to calculate the number of lottery combinations with repetition, and we can see that the total number of combinations jumps up to 220 because after we go and pick a ball, we throw it back in and we dramatically increase the odds that we could pick it again. Now what I'm going to do is analyze the number of possible winning hands we can expect in a game of poker. And just to make sure you're aware, there are 52 cards in a deck of poker cards, and there are 4 different suits: hearts, spades, clubs, and diamonds, as well as 2 different colors, being black and red. In this example, what I want to do is calculate the number of possible hands that provide 4 of a kind. And we're going to start off with the total number of suits, being 4. Then what we're going to do is pick the number we want 4 of a kind of from a total of 13 possible cards, ace the whole way up through king. That's 13 cards. And of course, there are 13 cards for each suit. Now, since we picked our value, we want 4 of a kind of, and we have that card for each of the 4 suits, we now must pick our 5th card. And there are only 12 cards left. So what we're going to do is multiply times 12. And then finally, to finish off, we must decide on the suit of our 5th card. And after we multiply all of the above together, we are going to find that there are 624 possible ways to create 4 of a kind in a game of poker. Now, whenever we are calculating the total number of full houses, we must use our combination formula. And the very first thing we're going to do is to pick the value. We want 3 out of a possible 13 cards. Then we want to pick what we want 2 of out of the remaining 12 cards. And now there are 3 ways out of 4 to pick the suit for our first 3 of a kind card. And we're going to use the combination formula to find 4 total combinations. Then we are once again going to use the formula to find 6 combinations when picking the suit for our pair of cards. And then what we do is multiply those together, and we find that there are 3,744 ways of getting a full house in the game of poker. We can then once again go in and divide by the total number of possible hands in poker, which is that big number you see down there in the lower right hand corner. And we can see that the probability of being dealt a full house is 0.14%. Now, very often you will come to the question of exactly which should we use. Well, basically, permutations are going to be used with an equal number of elements as well as positions. Combinations are going to be used when you only care which elements made it. And variations are going to be used when there are more elements than you have positions. So to provide another example, let's say we want to find out how many possible values we can use to unlock a combination lock. We take the number of elements to the power of the number of positions to get 1,000. And this is going to be done whenever we have repetition as a possibility. When you don't want repetition, you're going to use a completely different formula. And here what we want to do is find out how many variations of Pokemon cards can you create if you pick 3 cards from the total of 5. And if we plug those numbers into our formula, you can see that our final result would be 60 variations. Now, random variables are going to represent the results of your calculation. And there are 3 types, being finite, and you can see here in an example of a finite variable, the number of 6s rolled in 1,000 throws. We're also going to have countably infinite, which would be as if you would count the number of 6s rolled over the course of a year. And then you have uncountable infinite, which would be the number of 6s rolled on the entire planet Earth. And now we're going to talk about something called discrete uniform distribution. Now, a probability mass function is going to assign probabilities to random variables. Now, you know that a 6-sided die in any one roll has a probability of 1/6. And the most basic probability model is known as a discrete uniform distribution. An example would be a single die roll or a single coin flip. Now, to be a discrete uniform distribution, all possible values of x must be consecutive integers, like 1 through 6 with die rolls, and each value for x must have an equal probability of occurring. And to calculate the probability mass of a die roll, what we're going to do is just simply take 1 over b minus a plus 1, where b is going to be the maximum value and a is the lowest value. And for a die roll, that is going to equal 1/6. Now, variance is going to measure how far a set of numbers is spread out. And to calculate that, you're just going to take b minus a plus 2 multiplied by b minus a divided by 12, where again, b is the maximum value and a is the lowest value. And with a die roll, we can see that that works out to 2.9 or 3. Now, with this chart, you can see that it's going to provide the probability mass for each roll of 2 dice. A relative frequency histogram is going to show how often values are expected for each roll of those 2 dice. And this is what is called a cumulative distribution chart, which is going to provide the cumulative probability associated with adding additional possible dice rolls. And you can see here, as we add those, the percentages go up until we get here, finally, to 1, which would be 100%. Now, the expected value is going to be the long-term expected average, and it is found by summing all multiples of x by the probability of x. So for our dice rolls, that works out to 6.985 or 7. You can see over here that 7 has the greatest probability of occurring whenever you throw 2 dice. Now, calculating variance with multiple variables is a bit more complex. To do so, what you're going to do is sum the total of all values of x squared and multiplied by the probability. And whenever we do that, we get a value of 54.645. Then what we will finally have to do is subtract from that the square of the expected value calculated previously to get a final value of 5.855. Now, the standard deviation is going to be a measure of the amount of variation. And if that number is low, it means it is close to the mean average. If, however, it is high, that means it is going to be spread over a very large or wide range. And to find it, you just take the square root of the variance, which in this situation would work out to 2.419. Now, with a normal distribution in which we contain 100% of the probability under the curve, we also have an equal bell curve with the same area under both sides. We also are going to see here that the mean and median are going to be equal, and we also see that 68% of the total area is 1 standard deviation from the mean. This then is going to continue with 95% being contained under 2 standard deviations and 99.7% for 3 standard deviations. And this is known as the empirical rule. The empirical rule says that 1 standard deviation equals 68%, 2 equals 95, and 3 equals 99.7. And I further break that down here into all the different parts for all standard deviation distributions. Also notice that just 0.3% over here, or 0.15% on both sides, is all that is left after 3 standard deviations. And that brings us to z-scores. The z-score is going to give us the value in standard deviations for the percentile we want. And an example is going to make this very clear. So for example, if we want 95% of the data, it's going to tell us how many standard deviations are going to be required. And the formula asks for the length from the mean to x and then divides by the standard deviation. And now with this example, it'll all make sense. So this is a z-table on the right side of the screen. And if we know our mean is 40.8, as you can see down here, the standard deviation is going to be 3.5, and we want the area to the left of the point 48, so we want all this area. We perform our calculation to get 2.06. We can then find 2.0 right here. There's the 2. And then across the top, we can find 0.06, which is right here. And this is going to tell us that the area under the curve is going to make up 0.98, or 98% of the total area. We can also find the area to the left of the mean with a negative z-table. So if we want to find the area left of 36.3 with a mean of 40.8, we perform our calculation to get negative 1.29. We then look up negative 1.2 and 0.09 in the negative z-table, and we see that our answer is 0.09853. So the area under the curve from that point to the left is 0.098. Now let's go completely in reverse. Let's say I want to calculate the score I must get to score in the top 1% of my class. Now I know the mean is 0.79 and the standard deviation is 7.5. I then look for 0.99, which would represent top 1%, in the z-table to find the z-score of 2.33. 2.3 right there, and 2.3 right there, and 0.99, which is right there. Then if I plug that into our formula and solve for x, I find that I must score 96.48 to place in the top 1% of my test based off of all the supplied data. Now we have been using point estimates so far, which represent a singular point of data, and the mean would be an example of a point estimate. Now while point estimates are easy to calculate, they can also be very inaccurate at times. And an alternative is to use what we call an interval, or a range of values. So if I have 3 sample means taken from 3 different data sets, I can create an interval that covers their range of different values. I then have to find how confident I am in that interval, and we normally define normal confidences as 90%, 95, or 99. And this is going to mean that if we have a confidence of 90%, that we expect 9 out of our 10 intervals to contain our mean value. Now, when calculating our interval, what we do is we take our sample mean and find the values of x and y by adding and subtracting the margin of error. Alpha is going to represent the doubt that we have. So if we have a confidence of 90%, then in that situation, the alpha would be 10%. N is going to represent our sample size. And we were going to use, once again, a z-table to find our interval. So in this example, I've gathered all of our data, and if we look up 0.025 on our z-table, we get a value of 0.508, and if we plug that data into our formula, we find that x is going to equal 42.97. And then once again, we can also find that y is going to equal 43.029. And now we will move on to cover binomial probability. And it mainly is going to focus on whether we will or won't have a successful event. There are, however, conditions if you want to use this formula. First off, you must have multiple fixed trials with an outcome of pass or fail. The outcome of each trial can't affect any of the other trials. And then finally, the probability for each trial must be equal. So for example, if you are rolling one die 100 times and want the binomial distribution of rolling a 6, that is okay, mainly because you met all of our conditions. However, rolling a dice until you get 5 6s doesn't apply because the number of trials is not fixed. Here is the binomial probability formula, and you can see that n is going to represent the number of trials, r the number of successes, and we must find the number of combinations, and p is also going to represent the probability for each of those values. So what I want to do here is calculate the probability of getting exactly 4 6s in 10 rolls. First, we have to find the total number of combinations, and this is known as the binomial coefficient. Then we plug in the values, and we find that our probability is 0.048. And as we analyze our formula further, we can see the parts representing the probability of success as well as the probability of failure. Now, Poisson distributions are going to focus on the probability a specific number of events will occur over time or distance or area. For example, the number of visits to a website per day or hour, the number of pizzas sold, the number of red cars seen, vegetables expected for harvest, and so on. Now, the conditions to use this are going to include that you count occurrences over time, distance, and area. The mean occurrence must be the same over a similar time, area, or distance. The count occurrences over an interval can't depend on other intervals, and intervals can't overlap. In this example, if we can grow 6 heads of lettuce in 0.3 square meters, what is the probability we can grow 8? Now, lambda is going to be equal to 6, and if I plug in my values, I get 0.103 or 10.3%. And as you can see, the more x diverges from lambda, the lower the probability. It is important to make sure that x has a value no lower than 0. And then if you want to find the probability of getting at least 8 heads of lettuce, we're going to sum the probabilities for 0 through 7, and then subtract 1. We now move on to geometric probability, which is going to be used to calculate the probability of success depending on the number of trials. For example, how many dice rolls are required to get a 6? Now, the conditions for using it include that trials must be independent, outcomes are going to be either pass or fail, probability of success must be constant, and the number of trials need not be fixed like with binomials. And as you can see, we are multiplying the probability of success by the probability of failure to the power of the number of trials minus 1. Now, to find the probability of rolling a 6 in 3 dice rolls, what we're going to do is multiply the probability of a roll, which is 0.167 or 1 over 6, by the failure probability, which is going to be 0.833, 1 minus 0.167. And this is going to be taken to the power of the trials minus 1, like we saw previously. And you can see that that is going to come out to 0.116. And then if you want to find the probability of success in 3 or less rolls, what we're going to do is sum all previous probabilities, which is going to work out to 0.422. Now, we can also find the probability that it will take more than 3 dice rolls simply by subtracting the previous probability from 1. And we can calculate how many dice rolls it will take to get a success in this situation. And this is going to be called the mean. And we can see success is expected in approximately 6 dice rolls. And I'm also going to show here how to calculate both variance as well as standard deviation. And you can see those formulas right here, and this represents a square root. Now I want to briefly talk about sampling. Whenever we are gathering samples, it is important to follow the central limit theorem. Now the conditions of it are that samples must be random, the samples must be representative of the population, and that you use sampling with replacement, or that you sample less than 10% of the total population. And now we're going to go on and talk about negative binomial probability. Now, while the geometric model is going to find the number of trials required for success, or the number of dice rolls before you get a 6, the negative binomial model is going to find the number of trials until the nth success. So, for example, how many rolls are required until you get 3 6s? Now, the conditions to use this are that you must have independent random trials with either a pass or fail for all of the trials. The probability of success is going to be equal for each trial. And then finally, you must keep track of the number of trials up to the target success. Now, very often, the most confusing decision is based on which formula you should use and when. Now, the binomial model is going to be used when you want to count the number of successes with a fixed number of trials. The negative binomial model, however, is going to count the number of trials required to find a fixed number of successes. And then finally, the geometric model is going to be used to find the number of trials required for one success. And here you can see the formula for the negative binomial. In this situation, P is going to represent the probability of success, K is the number of successes I am to have, and N is going to represent the number of trials. Now let's say we want to calculate the probability of rolling 3 6s in 10 rolls. Well, first we have to find the number of combinations by taking 3 from 10, and this is going to be a situation where we will use repetition, and that is going to work out to the number 220. And then we just plug in all of our other values to find a total probability of 28%. And you can see here our probability of rolling 3 6s is going to be maximized at 15 rolls at 0.354. And then it's actually going to start falling. I don't know if you can really see it because it's very slight, but it falls dramatically more as we continue. And if you think for a minute why exactly that would be, well, the situation here is that our goal is to get 3 6s. However, at some point, we have an increased probability of rolling 4 6s, which is something that we do not want. And that's the reason why it starts to decline after 15. Now, a hypergeometric distribution is going to be used with samples without replacement to find the probability a specific number of items is going to fit a defined characteristic. With binomial and hypergeometric, you're going to find how many people have a characteristic, and replacement is going to define which of those that you are going to use. Now, the required conditions are that you sample without replacement, population has an equal chance of being sampled, population is also going to be in 2 groups, being those with the important characteristic and those who do not have it, as well as the number of people with the characteristic and the total population size must be known, and X is going to represent the total number of people you're interested in. And here is the formula we're going to use to calculate hypergeometric distribution probabilities. And as well, I provide a pictogram on the right side of the screen to try to explain the individual parts. So this is basically going to represent the whole entire circle here, is going to represent the total population. Then we have with M represented with successes, and minus M is failures. And then we have our sample being this small circle inside of here. And once again, the X represents the successes in the sample. And again, N minus X is going to represent the failures in the sample. And here I'm going to work through an example. So in this situation, what is the probability of getting 2 black cards if I draw 5 from a deck without replacement? Well, there are 26 possible black or success cards in this situation, and there are 2 successes in my sample. So the total number of cards is 52, if you remember from the number of cards in a pack or a deck of poker cards. And then finally, I'm going to draw 5 cards for my entire sample. Now this is a little bit complicated, but it's basically just calculating combinations down here and then bringing everything all together. And here is the main formula here. But basically, if I find the combinations for our formula we have here and work through it, you'll see that I have a 0.325 probability of success of drawing 2 black cards out of a total of 5 without replacement. And here what I want to do is calculate the expected value, which if you don't remember, is the number of successes you expect in the sample. And whenever I plug in the values, I get 2.5. And then I also will find the variance, which again is the average deviation from the mean over the long term. And if I plug in those values and work them out, you'll find that value is 1.15. Now moving on, to understand continuous probability is going to require us to cover a few other different definitions first. Continuous random variables are going to be variables with an uncountable infinite number of values. The probability density function is going to provide the density of the concentration of probability at any point x. And continuous uniform distribution is just a continuous random variable used when all the values of the probability density function are the same or are unknown. And this variable is going to be between 2 values being either A or B. And this is all going to make a lot more sense with an example. So I want to reiterate, a continuous uniform distribution is going to be used to find probabilities of success depending on all possible values between A and B. And it's going to be used to find probability for an interval rather than a point. For example, what is the probability that x is between the values of 5 and 6? I want to cover a couple more things, however, before I move on to that example. One thing to know is the domain of x is going to represent the interval that represents all the different possible values of x. And the probability is going to be the area under the curve. And this is called the density function of x. And some rules that we need to adhere to include that all values of fx must be greater than or equal to 0. And also the total area under the curve for all possible values of x are going to be equal to 1. And you can see here is the formula that we're going to use to find continuous probability for x in a given interval. And you can also see that you'll be able to find the value of b if you know both the height as well as a. And also, just to be inclusive here, I'm going to provide 2 just simple examples if you want to calculate probabilities when x is less than 3, or if x in this situation would be greater than 2, which are quite simple to calculate. And you can also see on the right side of the screen exactly how we would calculate these areas. So if we went from 0 to 4, and so forth and so on. And now to finish up everything, I want to cover a related topic, which is going to be exponential distribution. But before moving on to our example, I wanted to define exactly what an exponential function is. And simply, it is a function of the form ab to the power of x, where b is a positive number and x occurs as an exponent. An exponential distribution is going to be used for a continuous distribution, like we just saw previously in our last example, whose probability density has the shape of an exponential function. And this type of distribution is very often going to be used to model the time elapsed between events. Now, a density function of the form fx lambda e to the power of negative lambda times x, where x is greater than or equal to 0, and lambda is constant, is going to be representative of this density function. And lambda in this situation is going to be called the parameter of the exponential distribution. Now, a large lambda is going to cause the slope of the curve to drop quickly to 0, and vice versa. And like previously, the probability of an exponential distribution is going to be the area, once again, under the curve. And you can see here all of the different formulas that we're going to be using for exponentials. So less than x, greater than x, as well as how we will use x, or you calculate this probability in an interval. So let's say that I would want to come in here and I want to calculate the probability of getting home in 15 minutes. So if an hour is representative of 1, 15 in that situation would be represented with 0.25. Well, if I know my mean is going to be represented in which lambda is going to be equal to 2, where the mean is 1 over lambda, I can just simply plug in these different values into our formula. And remember, this is a less than situation. I want to see if I can get home in less than 15 minutes. And if I perform that calculation, you could see that I have a 0.394 chance of getting home in under 15 minutes based off of known information. If, however, I wanted to find out the probability of getting home after 15 minutes, using the same data from before and plugging it into our formula, you can see that it's much more likely that it's going to take more than 15 minutes, being that the answer comes out to 0.606. And like I said, I'm also going to be able to find probabilities in an interval. So if, let's say, I wanted to find out the probability of getting home between 15 or 40 minutes, if I just plug in those values, work the calculation, you can see that that comes out to 0.342. And then finally, to wrap up absolutely everything, if you would want to find the expected value for an exponential, all we would do is take 1 over lambda, which is going to work out to 30 minutes. And then once again, if we would want to find our variance, 1 over lambda squared, which is going to come out to 1/2 squared, which comes to 0.25. So there you go, guys. There is pretty much every formula I could imagine throwing into one course on probability. And if you guys like this type of tutorial, I was planning on also covering statistics, linear algebra, and calculus 1, 2, and 3. Like I said, if this is popular, I'll do it. Otherwise, I won't. And thank you very much for joining me for this really long course. And like always, please leave your questions and comments down below. Otherwise, till next time.